Hello students, welcome to the class. So today we will do the NCERT exercise of the chapter Chemical Bonding and Molecular Structure. So I've tried to put the questions such that you can get an overview of the overall chapter, right? So the questions will not be completely will not complete the whole exercise, but instead of that we will try to cover the greater part of the chapter through the exercise. Okay, so there will be questions from each and every theory. We will have questions from MOT, we will have questions from the hybridization, Vesper, and your Lewis dot structure. So this is the disclaimer. Now here is your first question. You have to discuss the shape of the given molecules. The molecules are BeCl2, then we have the SiCl4 and the ASF5. So three molecules are there. You have to determine the shape of that molecule. Okay, you have to use the Vesper model. Now we are already aware about the process to do so. So we first go through various steps, then we calculate the steric number, and lastly we determine the shape accordingly. So those who know it, you can start your answering right now. Meanwhile, I am solving it. Now, starting from the first step. So the first step would be identifying the central atom. So what would be the central atom if I am considering it for different molecule? So there is a very simple logic behind that. You will always take the least electronegative atom as the central atom until and unless your element is hydrogen. So if this element you are considering as less electronegative is hydrogen, then in that case you will take it as the surrounding atom. And apart from this case, whenever you see a less electronegative element, remember that you will put it as a central atom. Second would be drawing the Lewis structure of the molecule. Then third step is calculating the steric number. So this is the formula to calculate the same. So I will appreciate the part if you will try to determine the hybridization as well for the given molecules. Okay. Now in this formula, if you see the notations, then V is for the number of valence electron of the central atom. Then M is the number of monovalent atoms. So by monovalent atoms we mean those elements which have a valence of 1. After that we have C, which is the cationic charge, and we have the A, which is the anionic charge. The formula in total can be written as half into, then in the square brackets, V plus M minus C plus A. So what is the formula? We have seen it. Now we should know that how to predict the molecular structure or in the molecular shape using the steric number that we will get. So for each steric number there are specific, or I would not say a specific one, but there are 1 to 2 shapes that are possible. Now let us see different molecules one by one that are given in the question. So the first one which is given is BeCl2. If I consider BeCl2, then in this molecule beryllium is the least electronegative one, and therefore it will play the role of central atom. Now this will be the Lewis structure. It's very simple. Beryllium has 2 atoms. It will share both of its atom with chlorine, both of the chlorine, and form a single bond with both chlorines. Now here remember, it is a hypovalent compound because beryllium is still not completing its octet right now. Second thing is related to the steric number calculation. So we will use the formula, very simple formula, half into V plus M minus C plus A. So for the beryllium, the number of valence electron is 2. Number of monovalent atoms is 2 because chlorine has a valence of 1. So we will take both chlorine as the monovalent atom. Further, the charge is 0. It is a neutral molecule. So both the cationic and the anionic charges will be 0. Let us put all of these values in the formula. you will get your final numerical value as 2. There is only one shape which is possible for the steric number 2, given that there are no lone pair on the central atom, and that shape is linear. So we can finally draw the structure of BeCl2 as linear shaped. Okay, I hope you got it. So again, there can be one more question here, that what is the bond angle in case of BeCl2? It's very simple to determine it. Now moving on to the next molecule, which is SiCl4. So again, for the SiCl4, the central atom will be silicon because chlorine is a halogen. So it will be the most electronegative one in the given compound. So we'll take silicon as the central atom. Okay. Question is that how do we draw the Lewis structure? It's very simple. Just share each of the electron of silicon with each of the chlorine to make the final Lewis dot structure. Now one more question arises here. If you know the structure of SiCl4, so for those who have solved it, just predict the part that whether that shape will be ideal or not. Now what do I mean by ideal? So by ideal we mean that there should be no lone pair. Okay, and ideal means that the bond angle should be accurately that is in the actual tetrahedral structure, which is 109 degrees and 5 minutes. So if your SiCl4 is having a tetrahedral structure, so we'll see it will be tetrahedral, then is it ideal or not means the bond angle is 109 degrees or not. Okay, just check this thing. So it's a very simple method. There is a very simple method to check the same. You just have to look for the lone pair. Now moving on to the next part of the solution. What do we have? We have the calculation of steric number. So this is the formula: half valence electron plus monovalent atom minus cationic plus anionic charge. Now the number of valence electron is silicon is 4. We know it belongs to the carbon family. So it will have 4 valence electron in the valence shell. Further, the number of monovalent atoms will be 4 because chlorine is a atom which will have a valence of 1, so it will be a monovalent one. Then further, the charge is 0, the compound is completely neutral. So the steric number can be calculated as 4 plus 4 minus 0 plus 0 multiplied by 1 by 2, which will give you the steric number of 4. So if the steric number is 4, what will be the shape? Here the shape will be tetrahedral because it has no lone pair on it, and that tetrahedral will be completely ideal in nature. Now one more question for you. For the case of BeCl2 and SiCl4, what will be the geometry if the shape is already determined? So it's very easy to determine the geometry if you know the shape. Okay, yes, both of them will have the same shape and same geometry because geometry includes the lone pair on the central atom. As BeCl2 and SiCl4 has no lone pair on the central atom, therefore the shape and geometry will be same. Okay, now moving on to the next molecule, which is a molecule of arsenic. What about the electronegative element out of arsenic and fluorine? So for the AsF5, the fluorine will be the most electronegative one, and moving one step further, we know it already that fluorine is the most electronegative element in your whole periodic table. Okay, so there is no question about it that fluorine will be the one with greater electronegativity as compared to arsenic. Now coming on to the Lewis structure, there are 5 electrons on arsenic. Now the question is that how do we know it? So I have suggested you during the classification chapter that you should learn your periodic table group wise, and if you are aware about that, then the phosphorus falls in the same group as your arsenic, and phosphorus has a count of valence electron of 5. Therefore arsenic will also have a count of valence electron as 5. Now this 5 valence electron will be used by each of the fluorine to make a single covalent bond. Okay, so that, yeah, so the group of arsenic is 15. Therefore, the number of valence electron will be 5. Now, let us move on to the structure determination, where we will see the steric number calculation. We know the formula for the steric number. So again, the same formula. What about the values? So for arsenic, we know that the valence electron is 5 and the number of monovalent atoms is 5. Then we have the charge as 0. So we can calculate the steric number as half into 5 plus 5 minus 0 plus 0. That will give you the steric number total as 5. So if it is having a ASF 5, then what will be the shape? So the shape with 5 steric number and 0 lone pair will be trigonal bipyramidal. So this is the final shape of the ASF 5. I hope this is clear to you. Now one more question about this shape. So it's very important. How many angles are possible, bond angles are possible for the ASF 5 if it is trigonal bipyramidal? And what is the value of those angles? And third question, what will be the number of those angles? Again, I am repeating my question here, so you can think of it. Meanwhile, I am moving on to the next question. So what are the types of bond angles that are possible for this trigonal bipyramidal? Your first question. Your second question is, if there are 2 or 3, name them, and what is the count of each of the bond angle? Okay. So let us move on further. Now, if you know it, it's very easy, right? So let me tell it to you. So there are 2 types of bond angle. If you consider the fluorine which are present on the triangle, then each of this fluorine is making an angle of 120 degrees because 3 fluorines are there, right? So 3 angles are there. Now these 3 angles will be same, as it is an ideal case. No presence of lone pair is seen or no heteroatom is present. All of the atoms are same, which is fluorine. Now if it is the case, then 360 divided by 3 will give you 120 degrees. Okay. So this is the first angle which is possible. Then the next angle which is possible is 90 degree, which is between the axial fluorine and the equatorial fluorine. Remember which one is the axial and which one is the equatorial? We have already talked about it. So this one, which is linearly present, F, SF, F. So they are the axial fluorines and they are making an angle of 90 degree with the equatorial fluorine. So there are 3 120 degrees. And what about the 90 degrees? There are 6 90 degrees. So the up one fluorine is making 390 degrees with the 3 equatorial fluorine, and the downward fluorine, which is present in the axial position, is also making 3 angles with the 3 equatorial fluorine. So therefore, the total count will be 6 90 degrees. I hope this is clear to you. So it's very simple to understand. You can just try to draw the picture by yourself and look at the number of 90 degrees here. Okay. Now moving on to the next one. Here the next question says that the geometries of NH3 and H2O molecules are distorted tetrahedral. Okay, so this is a good question, right? So it is first of all considering the difference between the shape and geometry, and this is the only place where you will see in your books that there is a difference between geometry and shape, because if you consider the shape here, then the shape for both of this will be tetrahedral. Okay, not the tetrahedral. For NH3 it will be trigonal pyramidal, and H2O it will be bent. Okay, and the geometry for both of this will be tetrahedral, but the tetrahedral that we will see will not be identical in both of this. So there is a reason behind it. You have to think about that. So let us see what is the solution. If I consider the ammonia and water molecule, then this both figures can be imagined. Okay, you can try to draw it. It's very simple. Since it is a tetrahedral, you can draw it very easily. So if you look at this tetrahedral structure of ammonia first of all. Tetrahedral geometry of ammonia. Then in that tetrahedral structure, one lone pair is present and 3 bond pair is present. So nitrogen has overall 5 electrons, 2 are present as lone pair and 3 are used in bonding. So 3 bond pair and 1 lone pair. Okay. Now second thing, if you look at the water molecule here, then it has 2 lone pair and it has a bent shape. Okay, V shape or bent shape. Now why are we calling it bent shape? What is the logic behind it? Because if it is triatomic, then one more possibility is there, which is linear. So you take the case of CO2, it is linear in shape, but although it is triatomic, your H2O, it is not linear like your CO2 because of the presence of lone pair. It is bent. Okay, it is being bent by, or it is being moved by the lone pair. So that is the reason we call it as bent, or we also call it as V shape. So V shaped word is already justified by the shape that you are seeing for the H2O. Okay. Now in case of ammonia, it is seen that your angle is reduced from 109.5 degrees, which is the case for ideal tetrahedral, to an angle of 107 degrees. Similarly, here also in the water, the angle is changed from the ideal case to 104.5 degrees. What is the reason behind it? Because in the case of water and ammonia, we are seeing introduction of the lone pair. So 1 lone pair on nitrogen and 2 lone pair on oxygen. Now the question is that both are containing lone pair, then why is the angle reduction more in water? Because the count is more, and that extra count is creating an extra repulsion force on these 2 bond pairs, which is between both H and O. Okay, again I am repeating it. On the water molecule, we have 2 lone pair, which is creating an extra repulsion as compared to the ammonia, which has 1 lone pair, and as a result, your bond pair are moving much closer and the angle is decreasing to 104.5 degrees. Okay, so what you can say, that in case of ammonia, we have how many bond pair lone pair repulsion? We have 3 bond pair lone pair repulsion. In the case of water, we have 4 bond pair lone pair repulsion, plus we have 1 lone pair repulsion, which is between this lone pair and this one. Okay, and each of the respective lone pair is repelling both of the bond pair. That counts up to 2 bond pair lone pair repulsion, and that is the reason. So you can simplify this whole complicated term and say that due to extra number of lone pair, there is a increased repulsion, and that leads to decrease of the bond angle from 109.5 to 104.5. Okay, so I hope we are clear on the page of this question. Moving on to the next question. So it's very simple. It is related to the Lewis symbol term. You have to show the formation of cations and anions. In the case of potassium and sulfur A, calcium and oxygen B, and aluminium and nitrogen C. Just write the valency. Okay, just write the valency for it and you will get your thing. Okay, so it's very simple. So I will move through this question quickly. So first we will talk about the potassium and sulfur. We know that if I take the case of potassium and sulfur, then their electronic configuration can be written as 2881 for potassium and 286 for sulfur. So sulfur requires 2 electrons to complete its octet to make it 288, and your potassium needs to remove 1 electron to make it octet equals to 288. So that same will happen. So one of the potassium will donate 1 electron to sulfur, the second potassium will donate 2nd electron to the sulfur. In this way, your both of the potassium will have a octet, as well as the sulfur will also have a complete octet. Now moving on to the next molecule. No, I would not say a molecule. On the next ion. So the next ion is formed from calcium and oxygen. Electronic configuration for calcium and oxygen will be 2882. So it is belonging to the fourth period. Okay, so that is the reason we are getting this kind of configuration. Further, your oxygen will have 2,6 configuration, which is of second period. Therefore, we can say from the electronic configuration, oxygen will require 2 electrons to complete its octet, and calcium needs to lose 2 electrons to gain the noble gas configuration. Finally, we can show the electron transfer as from calcium, from one atom of calcium, we are getting 2 electrons, and that is the reason the oxygen's octet is being completed, and our complete molecule is formed as CaO. Moving on to the next question. So I will encourage more of you to give the answer. So the last one is related to aluminium and nitrogen. What will be the electronic configuration of aluminium and nitrogen? For aluminium, it will be 283, and for nitrogen, it will be 25. Now from the configuration, we know it very well that nitrogen will need 3 mole electrons to complete its octet, as it belongs to the group 15. Therefore, aluminium will lose these 3 electrons because it has 3 electrons extra than its octet. In this process, we know it very well now that aluminium will lose 3 electrons, and those 3 electrons will be gained by the nitrogen, which will give the complete formula as Al(N), where aluminium will have a 3 positive charge and nitrogen will have a 3 negative charge. Now moving on to the next question. Your question says that both CO2 and H2O are triatomic molecule, but the shape of the H2O molecule is bent, whereas the shape of the CO2 is linear. You have to explain this difference on the basis of dipole moment. So remember the question. Question is saying you to differentiate between the shapes based on the dipole moment. So first you try to know the dipole moment, then you move on to how do we differentiate between their shape. Okay, now talking about CO2 and H2O, we know it very well from our previous discussion that CO2 will have a zero dipole moment and your water molecule will have a net dipole moment which is not equals to 0. So let us try to see this thing and then derive at this final shape, that why the shape of H2O is bent and why for CO2 it is linear. So writing for that thing, we can say that in case of CO2, both of the CO bonds are equal and they will be opposite to each other. As a result, the net dipole is 0. And therefore, we can say that the CO2 is linear in shape. So see, we have a CO2 molecule which has a dipole moment of 0, which is representing that both of the vectors must have been cancelled out due to the opposite and equal nature. So if it is opposite and equal, therefore they are collinear. And hence we can say that the shape of CO2 will be linear. That will result in a zero dipole moment. Okay. Now let us see the case of H2O. If you consider H2O's dipole moment, then in the case of H2O, there is one lone pair present on the oxygen for one bond pair. Okay. Now both the OH are at opposite to each other on the other hand. Okay, they are not opposite to each other. That will result in a non-zero dipole moment. So let us try to understand this thing with the help of the bent shape of the H2O. So if you look here, then here both OHs are of equal magnitude, right? It is true. And the sign of the dipole moment will start from hydrogen and move on to oxygen, because oxygen is more electronegative and hence it will have a delta negative charge. Therefore, the direction of dipole moment will be from hydrogen onto oxygen for both the bonds. But these two bonds are equal in magnitude but not opposite in direction. So they are adding up and giving us a third direction of the dipole moment vector, which is being shown here. Okay. And this dipole moment is equals to 1.84 dB for the water molecule. Now, on this basis, we can clearly say that water is not linear. If it was linear, then its dipole moment would have been 0. But it is only seen for the case of carbon dioxide. Our next question is, arrange the bonds in the order of their increasing ionic character in the molecule. So, your molecules are LiF, K2O, N2O, SO2 and ClF3. Okay. So, just try this question out by yourself. I'm not letting you to know the answer. So, just try this out and do it by yourself. Okay, so this is a practice question for you. It's an easy one. So, I'm not dealing with it. Now, moving on to the next question. Now, this is a conceptual question. Now, why I'm putting this question ahead of you? Because this types of question may be asked in your reasoning type, right? So you have a question, not assertion reason type. Okay, so you have a type of your question in the MCQ, which is assertion reason. Question says that apart from tetrahedral geometry, another possible geometry for the methane molecule CH4 is square planar with the 4 hydrogen atom at the corner of the square. Okay, now you have to explain that why CH4 is not square planar. So 2 reasons are behind it. I will tell you the most dominated one. Then I will at last tell you that why the other shape is not possible. So there is one more reason. So let us try to understand it. So CH4 is not square planar. The reason is not of the absence of lone pair. It is not correct. Because the reason lie behind the inclusion of d orbital, or I would say the hybridization. So you must remember what is the hybridization for the square planar shape, and you will get your answer from there. Now coming on to the carbon, if you simply do the ground state electronic configuration of a carbon atom, so we can write it as 1s2, 2s2, 2p2. Upon exciting this carbon atom, we will have one unpaired electron present in each of the orbitals of 2p and 2s. So, for this given configuration, the orbital picture will look like this thing. Okay, so you can see that there is excitation and we have one electron in each of the orbital of 2s and 2p. I hope this part is clear to you. Now, if this is the case, then your hydrogen atom will donate its electron. I would say they will overlap with the orbital and share its one electron with the 2s and 2p only. So that will result in a sp3 hybridization. Okay, so finally we can write that carbon undergoes sp3 hybridization. As a result, it is having a CH4 shape. But the question is that why it is not square planar? Because for a square planar, the hybridization should be dsp2. So this is the required hybridization for square planar. And we know it very well that carbon has no d orbital or no d subshell. So therefore, question of square planar is completely ruled out. Okay. So carbon will have a tetrahedral shape due to absence of d orbitals. So we can say finally that CH4 cannot be square planar in shape. Now the second reason is also very true, which is the angle thing. Okay, so we know that in case of CH4 the bond angle is less, which is 90 degree, which will result in more repulsion. And you know that carbon atom is smaller in size, and this will not allow for this much amount of repulsion which is arising from the 90 degree small angle. So therefore it goes to the 109.5 degrees. So now the question is that if it is not for the small atom, then it should be true for the greater atoms, and yes, your assumption is true. So for the greater transition element, we see the square planar geometry. Now about that, we only see the square planar geometry in your 12th syllabus for your coordination compound when we see a D8 configuration. So we'll see this thing when we will study about the coordination compound. So there you will see that only few molecules are there which undergo the DsP2 hybridization to form the square planar complex. So nickel 2 plus is an example of that. Okay. So with some specific ligands, it is capable of doing a sp2 hybridization and the DsP2 hybridization, and therefore in that case only it is having a square planar shape. So it is NiCl4 2 minus. Now moving on to the next question. So the question says that which out of the NH3 and NF3 has higher dipole moment and why? So you have some time to think about it. Just see that what is the direction of dipole moment and you will easily get your answer. Just draw the shape, see the direction of dipole moment, and you will see that which of the two will have a greater dipole moment. So time starts now. I'm giving you 10 seconds approximately. Just think about it. Okay, so time is up. So let us look at the answer now. So both of them will have the same shape, of course, and they will have the same geometry, no question about it. But the question is that which one will have a greater dipole moment. I hope this answer surprises you, because most of the student must have made an assumption of making NF3 a higher dipole moment molecule, but that will not be the case. So let us look at it. Yes, it will have one lone pair and it will have one pyramidal shape. Okay, so if it is having a pyramidal shape, then we can identify the individual dipoles. So there will be dipoles along NH and it will have a larger net dipole moment. What is the reason? So for that, let us look at the picture of both of them. So first, if you look at the ammonia, then in the case of ammonia, the direction of dipole moment is starting from hydrogen and moving on to nitrogen. And that seems fair to us because hydrogen is less electronegative. It will have a delta positive charge. And we know that dipole moment starts from a positive part and moves to a negative part. Okay. Now out of nitrogen and lone pair, again, the lone pair will be the most electronegative one. So therefore, this lone pair will also have an upward dipole moment. So all of this are indicating an upward dipole moment. So in the last, these three NH3s will add together and that will result along with the lone pair in an upward dipole moment. Now this is the case for ammonia, in which all the dipole moment are kind of approaching in the same direction, and therefore NH3 is having a higher dipole moment in the resultant factor. But what about the NF3? The fluorine is the most electronegative one. Then the displacement of electron should be more. But we have a structural effect on this. And what is the structural effect? If you consider the NF3, then the direction of the dipole moment is just opposite for the NF bond as compared to the NH bond. Okay. So we can write that due to this cancelling out, we are seeing a small net dipole moment. How are we cancelling out? So for that, let us look at the picture. You look here. The nitrogen and fluorine will have a dipole moment direction opposite to NH. So it will start from nitrogen and move on to fluorine, because fluorine is the most electronegative one. Okay. Due to the lone pair, the dipole moment is upwards. Now you can see that in the case of NH3, the arrows were pointing on towards this upper arrow, and that is resulting in a total addition. Whereas in this case, you are seeing two opposite cases. The NF3s are pointing downwards somewhat, and the N and the lone pair are pointing upwards. So that leads to cancelling of somewhat dipole moment, and therefore we get a reduced dipole moment at the end, because the lone pair is indicating in a different direction, whereas your fluorine is indicating in a different direction. So that leads to the cancellation. Hence, we can say that NF3 will be less polar than the NH3, or it will have a less net dipole moment than the NH3. I hope this point is clear to you. Now let us move on to the next question. It's a good one. Is there a change in the hybridization of boron and nitrogen as a result for the following reaction? So in this reaction, what is happening? The boron will be sp2 hybridized, okay, in the BF3, and in the ammonia, the nitrogen will be also sp3 hybridized. You can try to calculate the steric number and you will get in the hybridization as well. Now, if this is true, then after the reaction, what will happen? The nitrogen, which is a basic one, okay, it is a base because it is having a lone pair, whereas the BH3, which is a Lewis base, with Lewis acid. Why it is a Lewis acid? Because boron has a hypovalent octet. Remember, it is making only 3 bonds, so it will be lack of electron, and these electrons will be donated by the ammonia. So this donation will result in an adduct. In the formation of an adduct, you can see it, that the nitrogen pairs are being donated onto boron. Now, as a result of this adduct formation, your boron is making an extra bond, which is changing the hybridization of boron from sp3. Okay, so whenever it will get electrons from other atom, it will have a charge, and this will create a sp3 hybridization on the boron, because now it is making 4 bonds, so 4 is the steric number. But in the case of nitrogen, the steric number is still same. Instead of the one lone pair, we have a BH3 attached to it, and that will result in no hybridization change in case of nitrogen for the adduct that is formed. So this question is somewhat easy but quite difficult to understand, right? So just think about it as a completion of octet for the boron, but since your boron is not getting any you can say an increase in the number of bonds, it is getting an increase in the number of bonds, so therefore its hybridization is changing from sp2 to sp3. Whereas your nitrogen, which has the same number of bonds and the lone pair, so if you count the number of bond pair plus lone pair, it is same for the adduct also. Therefore, it will have a unchanged hybridization. Okay. Now, our next question. So we have to decide that why the Be2 is not existing using the molecular orbital theory. So I am giving you some time to solve it. So after that, we will see the answer. So you have 10 seconds approximately. Just try to solve it. That what will be the bond order? What will be the existence nature, dimagnetic nature if it is existing, right? So your time is up. Let us see. If we look at the electronic configuration of beryllium, then it is 1s2, 2s2. So we can write the molecular orbital electronic configuration as follows. So sigma 1s will have 2 electrons, sigma star 1s will also have 2 electrons. Then sigma 2s will have 2 electrons, sigma star 2s will also have 2 electrons. So total of 4 electrons were there in one beryllium atom. So that will result in total of 8 electrons in the beryllium molecule. Okay. Now, what will be the bond order from this diagram? So 4 electrons are there in the bonding and 4 are there in the anti-bonding. Therefore, we can write NB is equals to electrons in bonding molecular orbital. We know that in this formula. And for Na is the anti-bonding. And finally, the bond order will be half into 4 minus 4. So this will give you the bond order of the beryllium. Now there is a shortcut to calculate the bond order. So we'll now talk about that shortcut. For that, you have to only remember the bond order for the nitrogen. Okay. So it's very simple. You just have to, what you have to remember to know the bond order of nitrogen. So what is the bond order of nitrogen? Think about it. It's very simple. What is the bond order of nitrogen? Yes, for the case of beryllium-2, there will be no existence because the bond order is coming out to be 0. So if you see the nitrogen molecule, then it has a bond order of 3. Okay, it has a bond order of 3. Now suppose you know the bond order of nitrogen and you want to know it for the oxygen. Right? Very simple. So you are moving one step ahead of nitrogen. Now the bond order will be reduced by 1 unit. How? So from nitrogen it is 3, then for oxygen it will be 2. Now what about the boron? If you calculate the bond order of boron, it will be 1. No, not for the boron. Boron molecule, it not be 1. So what will be the bond order of boron? Any guesses? So again I am repeating it, just think about it. So what will be the bond order of boron? It's very simple. Yes, it is 1. Now you come on to the next molecule, which is carbon. So in case of carbon, the bond order is 2. Now what is the trick? It's very simple. Okay, the trick says that if for nitrogen it is 3, you move 1 ahead. Oxygen, the bond order reduces by 1. Now you go back from boron to from nitrogen to carbon, then also the bond order will be reduced by 1. So that's the simple idea to remember it. Now you go from carbon to boron, the bond order will be again reduced by 1, which will be 1 for the boron. So you start from boron, move on to nitrogen, which is 3 maximum, and then you again go on decreasing the bond order. For oxygen, it is 2. Then after oxygen, we have the fluorine, which is again having a bond order of 1. Okay, so it's very simple to remember it. You just have to remember it for the nitrogen. And if you are moving one step further, the bond order is reduced by 1. If you are moving back step in your periodic table, then again the bond order is reduced by 1. And this thing is being followed. So if you are clear about it, very well. If not, we can talk about it later. Now moving on to the next question, the last one, which is description of the hybridization in the case of PCl5. And you have to also tell me that why the axial bonds are longer as compared to equatorial bonds. We have already talked in a much detailed manner about the same thing. So first, let us try to determine the hybridization of PCl5 and look at the shape of the PCl5. If you look at the PCl5 molecule, then its outer electronic configuration will be like this. Okay, so 3s2, 3p, 3. Why? Because it belongs to the 15 group. Now, we will excite the phosphorus molecule electrons. Remember students, excitation is never a strong criteria or the most, or I would say, the only criteria to excite the molecule. You cannot excite it in every case. So remember this thing, that the excitation of electron is not a necessary condition for the case of hybridization, but we do it for most of the cases, but still it is not the case for every molecule. In this case, there is excitation. The 3s electron are being unpaired up and we are seeing an electron that is jumped onto the 3d. Now sp3d will be the hybridization. Therefore a chlorine atom will donate its electron, I would say it will overlap with the sp3d hybrid orbital, and that will result in pairing up of the electron of the phosphorus excited atom. Okay. Now, here there are 5 orbitals. 1 is of S, 3 is of P, and 1 is of D, which is available for hybridization, and that will give you a hybridization of sp3d. if you look at the shape of the trigonal pyramidal, according to the PCl5, then it will have chlorine atom on the 5 corners of the trigonal pyramidal. So this will be the shape, which is trigonal bipyramidal geometry of PCl5. Now the question is that, what is the bond angle? So the bond angle is not equivalent for all of the cases. So there are two types of bond angle, 3-120 and 690. And the next thing is that the bonds are also not equal. Okay, now let us look at the bond length. So what is the bond length comparison of both of the bonds, which is axial and equatorial? So for the PCl5, the axial bonds are having a greater length as compared to the equatorial bond. Now what are the equatorial bonds? So these are those bonds which are being formed on the equatorial plane, which is a triangle. So 3 equatorial chlorines are there. Therefore, these 3 chlorine atom will make a shorter bond as compared to the 2 axial phosphorus chlorine bond. Why it is happening? It is happening due to the repulsion. So 3 repulsions are coming, and as a result of this 3 repulsion, which is coming from the 3 equatorial plane, the chlorine atom is moving away from the phosphorus to minimize the repulsion, and this creates a weaker, slightly weaker axial bonds. I hope this is clear to you. So this was all for today's lecture. Thank you.